Up to now, all our signals have been unsigned. To use a signed signal, be it a wire or a reg, we need to use the keyword signed. So for example, if we've got reg 5 to 0 A, we are creating an unsigned vector of type reg. To create a signed vector, we use the keyword signed in this way. And now we have a signed vector of size 6 bits of type reg. So the keyword signed results in the variable a being a signed quantity. The signed keyword can be used with variables of type reg or of type wire. So in our example, a and b are declared to be signed variables of type reg of size 5. So we've got a and b, signed variables of type reg. Looking at our initial block, we assign the values -3 and 2 to a and b respectively. And that's carried out in the same way as on previous slides. So we've got the value 1, 1, 1, 0, 1 and 0, 0, 0, 1, 0 for a and b. Now because a and b are signed, value for a is interpreted as a signed value, and it actually represents the value -3 decimal, and b is 2 in decimal. Now that we're dealing with both signed and unsigned signals, we have to distinguish between them in our expression tree. So in the case where we've got both signed and unsigned, we're going to use S to indicate signed and U to indicate unsigned. For our first example, we'll take this assignment and look at the expression tree for it. Our first step is to identify the sizes for the quantities in the expression. So we've got 5 for A and 5 for B, and the left hand side of the assignment, in this case D, is of size 6. You can see D is a 6-bit vector of type wire. So now that we have our sizes, we take the larger of those 3, and that's 6, indicating this is a 6-bit addition. As noted, we now need to keep track of what's signed and unsigned. A is signed, B is signed, and D is unsigned. Given that the addition is a 6-bit addition, our output is 6 bits. And therefore we need to extend our 5-bit input to a 6-bit input for both operands. And this time the extension is a signed extension. In our previous examples we had unsigned extensions, which we denoted with U. Here we have signed extensions, and a signed extension produces a signed quantity. So our two inputs to the addition are signed, and therefore the output is a signed quantity also. Let's work through the operation with the values we've got. So for A we have and B. To extend the value 11101 from 5 to 6 bits, we take the value and we have to create a 6th bit. For a sign extension, the way in which this works is that the MSB of our 5-bit value is replicated to create our extended value. The most significant bit, our MSB, is a 1, so we replicate the 1. And this is our 6-bit value. We do the same over here, take our 5-bit value. We need to extend that to 6 bits, so we need 1 extra bit. And because we're doing a sign extension, we look at the most significant bit, which is a 0, and we replicate that. These are our two values we now add. And when we add them, this is our result, which is the output of the addition. It's a 6-bit value and it's a signed quantity. So if you want to interpret this in decimal, that's equivalent to -1 in decimal. Our final step then is to assign this 6-bit value to this 6-bit value for D, and that's easy, both are the same size. And taking this as our LSB, we'd start with our LSB here and make the assignment. Now you'll note D is unsigned, and we cannot change from an unsigned to signed type. D, when declared, is unsigned, and it remains unsigned. So that means the value for D, because it's unsigned, in decimal is 31 decimal. Now when we take an assignment in Verilog, we've got something like this. The left hand side is equal to the right hand side. So we've got an expression on the right hand side, and in the case of a continuous assignment, we've got a wire on the left hand side. This is our left hand side, and this is our right hand side. So when we work out the size of the addition operation, what we did, we looked at both the left and right hand side. When determining the size for the arithmetic operation, we know that it's context determined, and we looked at the sizes within the expression and the left hand side. So in our example, we looked at the sizes 5, 5, and 6. When it comes to determining the sign for an arithmetic operation, Verilog only looks to the right hand side. So for the sign, we do not consider information on the left hand side. Even though the sign for the left hand side in our example is unsigned, this does not influence whether the arithmetic operation is signed or unsigned. So for the arithmetic operation, only the right hand side determines the sign for an operation. And the way it works is that only when all operands are signed is it a signed operation. And a signed operation produces a signed output. Here is another example, and this time we take this assignment. A and B have the values shown, and the expression tree looks like this. We start by identifying the sizes of the operands in the expressions. So we've got 5 and 5 for A and B, and the left hand side, it has a size of 3 bits, and our left hand side is E. Next, we determine what the largest size is. So we've got 5, 5, and 3. The largest of these 3 values is 5. So that makes this a 5-bit addition with a 5-bit output. Next, we need to determine what's signed and unsigned. So both A and B are signed as specified in the declaration for A and B, and E is unsigned. So remember, when determining the sign for an operation, the left hand side does not impact that determination. Both operands for the addition are signed, so this is a signed addition. And that means the output is a signed value. We don't require sign extension in this example, as the operands are the same size as that specified by the addition, 5-bit. We can quickly work through the calculation. These are our input values. The values are added to produce this value, and that's the output of the addition. And E in this case is a 3-bit wire, so the lower 3 bits are assigned to E, and we lose the upper 2 bits. And for the last statement, which is this statement here, we have the following expression tree yielding a 7-bit addition. We have sign extension yielding 2 signed values and a 7-bit signed output for the addition. Sign extending this 5-bit value, we have the following: 1, 1, 1, 0, 1, and we need to extend it from 5 to 7 bits. We therefore require 2 additional bits. So remember, for sign extension, you take the most significant bit, which in this case is a 1, and replicate that, yielding the following. So our value now is 1, 1, 1, 1, 1, 0, 1. And for our second operand, we need 2 additional bits. It's a signed extension, so we take the most significant bit of our 5-bit value, which is a 0, and replicate that value. So these are the 2 7-bit values that we add. We get a 7-bit result here, and we assign those 7 bits to F.